Lecture called Physics is All About Moments says one way to keep momentum going is to constantly have greater goals by Michael Korda. Like we said, this is the lecture that's introducing you to the concept of momentum. So let's go ahead and get started. The goals are that you be able to differentiate between inertia and momentum. Now, inertia is something that we talked about earlier this year when we talked about force, and you should also be able to distinguish these between momentum and what inertia is. The second thing is we want you to be able to relate momentum to force and motion. So we want you to be able to kind of interplay those two and see where they come from. And thirdly, we want you to be able to use the equation P equals mv, which is one of the main equations that you'll be using in this unit. Okay. Now, in the investigation, what you did is you rolled a car down a ramp and you were trying to figure out how difficult it was to stop the momentum of a car. And what you should have seen is there's a couple of different factors that affect the impact on this particular styrofoam block. Okay, the first thing is easy, it was the mass of the car. If you added more mass to the car, there ended up being a greater impact. Okay, there ended up being a greater impact um, on the styrofoam block. So more mass equals a greater impact. Okay. Secondly, you should have seen that if you allow the car to move further, so in other words, if you started it here versus if you started it here versus if you started it here versus if you started it here, the further back on the track, the greater the impact. So we're going to say the greater the distance, the greater the impact. I'm going to call it impact. Okay. And thirdly, you should have seen that if you were to take a look at the angle, so if you were to take a look at the angle between the ramp and the ground, as you increase this particular angle, so in other words, as you increase the angle, you also increase the impact. So there's a couple of different things that affect this impact. Now, how are angle and distance related to the speed of a car using kinematics? Well, we've talked about this before with several labs that we've done before, but as you increase this particular angle, what you're really doing is you're increasing the acceleration of the car. Okay? And as you increase the distance that it rolls along the track, okay, that's the distance that it's accelerating. So these two variables are actually increasing the distance and the acceleration. Well, if you combine that with the fact that you have an initial velocity of 0 to begin with, now you've increased the acceleration and you've increased the displacement or distance as the initial velocity is 0. So really what you're doing here is you're doing two things. You're increasing the time the ball or the car rolls along the track, which is not particularly useful. And you're also increasing, and this is the key one, you're increasing the final velocity. So you're increasing the velocity as it strikes the styrofoam block. So really we're doing two things here. One thing is increasing the mass increases the impact, and the other is increasing the velocity at which it strikes the styrofoam block increases the impact. Now, this impact term is actually what we talk about as momentum. Okay, momentum is sometimes referred to as mass in motion. Okay, so it requires two things. It requires, number one, that it have mass. Okay, that's not a hard thing. Everything that we talk about has mass. Okay, down from an atom all the way up to a universe, everything has mass. Now, the other key thing is that it's mass in motion. So whenever it's in motion, it must have some sort of velocity. Okay, if you have those two things present, if you have mass and you have velocity, then you have momentum. Now, because of that, a lot of times you'll see momentum referenced with energy. So you should be able to say, okay, well, if it has to be in motion, that means what type of energy does it have to have? And I'll leave that for you to figure out, but it's either gravitational potential energy, kinetic energy, or elastic energy. There are situations in which it can have all three, but no matter what, if an object has momentum, it should have one of those. Now, momentum is defined as the product of the mass and velocity. So, since it's the product of those two things, if you increase one and decrease the other, there's really no change in the momentum. So, really, you need to increase both if you want to increase momentum by a great deal. So, like I said, we have to have both mass and motion, and that momentum is a vector quantity, which means that it is very important that you specify the direction. So, whenever I say it has a momentum of 10, and you'll see this later, kilogram meters per second, you really should put a direction like east or west or positive or negative. What this means is because it has direction, you are also going to have values like negative 10 kilogram meters per second. And you need to keep those in perspective because these have the same magnitude, but they're in opposite directions. So you make sure you keep that straight and make sure you realize that momentum is in fact a vector quantity. Now, As far as rehashing what inertia was, we said inertia is the tendency of an object to resist a change in motion. So here we have momentum, which is mass in motion, and inertia, we have the tendency to resist motion. So a lot of times people will substitute the idea of mass for inertia. Now, as long as we're looking at it in terms of straight line motion, that works pretty well. If you start to get into things that rotate, that's not quite a great analogy, but it works for our purposes right now. So inertia is the tendency to resist a change in motion, okay, whereas mass times velocity is the actual momentum. They are different quantities. So inertia does not require an object to be moving. If you have a boat, okay, you can see my great drawing of a boat. If you have a boat that's sitting in the harbor, if that boat is not moving, it still has inertia, okay? It still has a resistance to a change in motion. So if I come and try and push the boat, it's not going to move very much because it's resisting the change in motion. Now, if you were to have this boat that's sitting in the harbor, it would have zero momentum because it doesn't have any velocity. The momentum equation that we have is P equals mv, where P is actually a Greek letter rho, but it looks like a P. So really you should think of it as kind of a lowercase rho, because P is going to stand for power and all sorts of other things. But this really is momentum right here. Now momentum is mass in motion. It is the unit of kilogram meter per second. Now a lot of times you'll see it as kilogram dot meter per second, and really that dot is just indicating that those two things are kind of multiplied together. You cannot directly measure momentum. Okay, you can measure the mass, you can measure the velocity, and you can calculate the momentum, but as far as direct measurement, you can't really do that. You can also measure the momentum by impacting something that we'll talk about later, but once again, you're measuring the impact and calculating something out. You can't directly measure momentum. Now, mass we've talked about a great deal. Velocity we've talked about a great deal. It's kilograms, it's meters per second. You can measure them with radar and meter sticks and photo gates and all kinds of things, but you should be familiar with all of those by now. It is very important that you realize that the mass needs to be in kilograms. That's a lot of times what people forget to do is they'll say, oh, I have the mass of a bullet that's being fired into wood. What is the momentum? And you forget to change the mass from grams to kilograms. So just be aware of that. This first example says, determine the final momentum of a bike rider who is initially traveling at 4 meters per second, then subjected to the free body diagram below for 10 seconds. So the first thing that we want to do is we want to say, okay, if I'm trying to solve for the final momentum is going to be the mass at the final and the velocity at the final. So those are the two things that I need in order to make this work. So if I were to look at this particular situation, I would realize that no matter what forces I exert on a particular object, the mass is not going to change. So the mass is going to stay the same regardless. So really what I need to do in order to get this to work is I need to solve for the final velocity. So the first thing that I need to do is I'm going to go ahead and work through these forces and kind of see what I've got going on. The first thing is if you were to look at the free body diagram, you would say, okay, the normal force and the gravitational force are equal and they cancel each other out. Okay. You also have the fact that you have a frictional force and an applied force, and those don't quite cancel each other out. And what they leave you with is they leave you with a combined sum of the forces of 10 newtons, and it would be to the right. So you have a combined forces of that. Using the sum of the forces, I can calculate the acceleration of this particular object, and what I can do is I can say, okay, the sum of the forces is equal to the mass times the acceleration. Well, in order to do this, I need to know the mass. Well, remember, if you have the weight is equal to mass times gravity. There's a lot of review going on this particular example. So what I can do is I can say, okay, well, if I have a weight of 490 and I'm on Earth where gravity is 9.8, you can go ahead and say, okay, well, then the mass is 50, and the mass is 50 kilograms. So now I can go ahead and say, all right, well, if I have a sum of the forces of 10 and I have a mass of 50, that allows me to solve for A. And A in this case would be 0.2 meters per second squared. Now with an acceleration of 0.2 meters per second squared, you can now say, okay, well, I've got the initial velocity, and that was 4 from the problem. I've got the acceleration, which I calculated to be 0.2 meters per second squared, and I have the time to be 10 seconds. Using those three things, I can use my kinematics motion equations, and I can solve for the final velocity. Now if I were to do if dat, I, F, dat, I have the initial, I have I'm looking for the final, I have the time, and I have the acceleration. So the only thing that I don't have and don't care for would be the displacement. Well, that means the equation that I would choose would be final velocity equals initial velocity plus acceleration times time. Or in our particular case, I would say the initial velocity is 4 plus the acceleration is 0.2 times 10. Looks like I'm running out of room here. So you would multiply 0.2 times 10 and you get 2, and then add it to 4, you would get a final velocity of 6 meters per second. But remember, this is not what you're looking for. You're trying to solve for the final momentum, which means you need to take the mass, which we conveniently have right there, and we have the velocity, which is right there, and we need to plug them in, and we need to be able to solve for momentum equals mass times velocity. So we plug our values in, and when we do that, we get 50 times 6, which is 300 kilogram meter per second. Okay, that example had a lot going on. We had to read the free body diagram. We had to solve for the mass using the gravitational formula. We had to then plug our variables into the kinematics equation. Once we plugged them into the kinematics equation and solve for final velocity, then we had to use the momentum equation. So you can see there's a lot going on in this particular example. Now, most of the momentum questions you see aren't going to be that difficult. If you look right here, it says a car is released from rest and allowed to roll down the ramp until the styrofoam block is shown. It says sketch the relationship between the distance the car is allowed to roll and the momentum of the car as it reaches the bottom. This is a little bit more complicated than it looks. So first of all, we need to label our axes. So this is going to be distance, and we'll call it meters, and this is going to be momentum, and we'll call it kilogram meter per second. So if we were to look at this, we have the equation that momentum equals mass times velocity. Okay, and that's really good. In this case, it's going to be the final velocity because you're looking at the momentum as it impacts. Now, the problem is that distance is not anywhere in this equation. So what I need to do is I need to be able to figure out a way to get distance in that particular equation, but I need to make sure that my variables are all consistent. So because I'm leaving the track at a constant elevation, I can say that the acceleration is a constant. I'm going to be releasing the car from rest, so that right there is going to allow me to say the initial velocity is 0, which is also constant. Using these things, I can also incorporate the distance formula, and I can say, okay, final velocity is equal to squared is equal to initial velocity squared plus 2AD. Okay, you may be thinking, okay, well, how is this related to whatever I'm trying to do here? What I need to be able to do is I need to be able to say, okay, I need to substitute something with distance in to this particular equation. When I do that, I'm going to end up getting something that looks like this. I'm going to substitute in P is equal to M, same thing here, and now I'm going to substitute in what VF actually equals, which is going to be the square root of VI squared plus 2AD. Now, when you are graphing two variables, the only thing that matters are those two particular variables. So, I can say mass is not on this graph, so it's irrelevant. It doesn't go away, it's just kind of a constant at this point. It becomes a regular number. Same thing with initial velocity, which I know is 0. Okay, 2 is a number, and then acceleration is a constant number as well. So those kind of go away in terms of the graph. Now, if I was calculating this out, I couldn't do this. But it's one of those things. This is a graph, and it's very different. So now what I end up with is P is equal to, or we wouldn't really say equal at this point. We say P is proportional to the square root of the distance. Okay? If you have P is proportional to the square root of the distance, you can now substitute in. You can say, well, P is on the y-axis, so I can say y is proportional, in this case, to the square root of x. So what I can do now is I can say, okay, my graph is going to say y equals the square root of x. So if I were sketching the graph, it would look something like that. Now I know it's not going to be perfect in terms of it's going to be exactly proportional to that because we have those constant numbers that we threw out. But those constant numbers will either raise the graph or lower the graph, but it will maintain its same shape. So if you look, as you increase the distance along the ramp, you're not having the same proportional increase in the momentum. And the reason why is by increasing this distance right here, you're not really affecting the velocity as much as you normally would. And if you're not increasing the velocity in a direct relationship, then you're not increasing the momentum in a direct relationship. This is a tough question because it requires you to know a lot of things and pick the right kinematics equation. If I would have picked a different one, it might have showed a different relationship, but I can't do that because a lot of people will say, oh, well, time is constant. And it's not, because if you start the car here and you start the car here, it's going to have different times to get there. So I couldn't use one of the equations with time in it. Like I said, this is a tough question, one you really got to be able to think through. This one is a little bit easier. It says determine the momentum of a 5 kilogram bowling ball thrown at 14 meters per second. So we want to go through the guess method as we normally do. We say mass is equal to 5 kilograms. We say velocity is equal to 14 meters per second. The equation or what I'm trying to solve for is I'm trying to solve for the momentum. So I've got my given and my unknown. Now I can substitute my equation in there, P equals mv. Once I've done that, I can now take these and I can plug them in, and I can say 5 times 14, and that equals 70 kilogram meters per second. So that right there represents the momentum of this particular ball. Now really I should have a direction here, and based on the picture I want to say left, because I'm going to assume that the velocity was to the left based on this particular picture. So now you should have a pretty good grasp of what momentum is, and you should be able to calculate momentum, velocity, mass, given those appropriate variables. And you should also be able to do the things with a graph and relate all our kinematics motion to these things as well.